inverse function. An inverse function is like a reflection of the given function. So the easy way to remember this is just by interchanging your x and your y variables. Again, interchanging your x and y so you can get the inverse of a function. If you're given with ordered pairs, example, you have here set of ordered pairs like 1 comma 2, then you have negative 3 comma 1, and then you have, let's say, 5 negative 4. Okay, the inverse for this one, you just actually switch the value for x. So that would be f inverse, that's a power of 1. And you will just switch the values for x and y. So you will have like 2 comma 1. And then here it's 1 comma negative 3. Again, you're just interchanging your x coordinate and the y coordinate. So on the third order pair here, it gives you negative 4, 5 by interchanging the values for x and y. So that's how we find the inverse. If you're having an equation like f of x equals 2x plus 4, finding the inverse of this one, we know that f of x is our y here, is equal to 2x plus 4. The first step is interchanging our x and y. So interchange x and y. By doing that, you have, instead of writing your y here, you put x. Then instead of x here, you have y. And then you solve for your y. So moving my 4 from right to left becomes a negative 4. And you have 2y left on the right side. And we divide all terms by 2, so we can solve for y here. So the next step is solving for y, or solve for y. So this cancels out. Our y therefore here is equal to x over 2 minus 2. And that's our inverse. So we can write our inverse as our final answer as f of x power of negative 1. That's the symbol, equals to x over 2 minus 2. So that would be the inverse of function f of x is equal to 2x plus 4. Okay, so let's say you take the inverse of y is equal to x over 2 minus 2. Your answer would be the given one. It will go back to f of x is equal to 2x plus 4, because those two equations are the inverses for each other. Another way to look at this also, we can have another one here. So if I'm going to write this, let's have an example here. Let's use the same f of x, which is 2x plus 4. And let's say the inverse, we put that as g of x. And our answer a while ago, it's x over 2 minus 2. Okay, and we know that these two functions are inverses to each other. Um, we can actually prove this by composition. So it's like if you have f of g of x, our answer here would be x. Okay, and if you do that, um, we're moving our g of x here, going to our f. So our g of x is x over 2 minus 2. So if I have this, I will have, so this is our answer if they are inverses to each other. So 2 times x over 2 minus 2 plus 4. Okay, so let's multiply this, and it gives us x here. Multiplying this by distributive property, it's a minus 4 plus 4. So our f composition of g of x, so negative 4 plus 4, this cancels out, this is 0. So the answer is x. So you can see that it go back to x here as our answer if they are inverses to each other. Same thing if you do like g of f of x. So this is just similar. So the answer should be x. So we can try that by plugging in f of x, our value for x in g of x. So we are looking at this g of x here, and we plug in our x there, which is our f of x. That's 2x plus 4 over 2, and that's minus 2. Okay, so simplifying, we will get g composition of f of x is equal to 2x divided by 2 is x, then 4 divided by 2 would be a 2, so, and then minus 2. So therefore our answer would be just x, since 2 here will be cancelled out. Okay, as you can see, the x here is exactly the same x as we have it here. Okay, so we have the x and the x here. So that's how we know that they are inverses to each other. If the answer is not x, then it means they are not inverses to each other. So that's by using composition to show you if they are inverses or not. Okay, let's show you another way also. So let's use the same two functions, f of x, 2x plus 4, and g of x equals x over 2 minus 2. Okay, so we know that we proved this a while ago, and these two functions are inverses. Another way to prove this also is by assigning a value, like you have to evaluate a value. So let's assume x here is equal to 2. for f of x, that would be f of 2. And we have 2 times 2 plus 4. So our answer here is 8. And we're going to use that value as the value for x in our g of x. So having that, we have g of 8 here. And we have to replace our x with 8. So 8 divided by 2 minus 2. So we will have 8 divided by 2, that would be 4, minus 2 is 2. So as you can see, the value that we assign at first is the same as the outcome here. So if they're exactly the same, then they are inverses to each other. So that's how we get that one. Even if you flip this, you try g of 2 first, you will get the same value going to your f of x. So that's how we test if they are inverses or not. Another way to know if they are inverses also is to use a graph. So if you're using a graph here, if you're looking at this equation, that's a line, and this is a line also. So this line here, the reflection of this would be this. So the reflection line is y is equal to x. Since, as you can see a while ago, that when we do the composition, it's always x is the answer from the previous example. So we can show that now using graph to illustrate the inverses of two functions. Okay, so let's share the graph. Okay, so looking at the graph now, this is our f of x is equal to 2x plus 4. That was our example. And this is our g of x, x over 2 minus 2. So we got this by taking the inverse of the first function and then switching the x and the y. So we're interchanging the x and the y. So we're getting this value here. So observe that there is an intersection here between the two. So the red one is the original function, and it is reflected on the other side. And the reflection line is y is equal to x. So observe that y is equal to x. It's the common intersection between the two functions. So let me change the color of y is equal to x. So as you can see that's the reflection line. So if we interchange the value for x and y, then that's exactly the same thing here. So as you can see, when I'm going to look at this point here of our y-intercept, that's 0, comma 4 for the first function, which is the red line. And when it's reflected on the other side here as the x-intercept now, it actually interchanged the value. So that's exactly what we did a while ago. So that's 4, comma 0 now instead of 0, comma 4. So the line at the middle here, it's the reflection line. And if you think about line of symmetry, you can see that also. From this point, from here going there, it's exactly the same distance from here going to the other point, which is 4, comma 0. So that's exactly the definition of line of symmetry also. So think about when you take the inverse of a function, The requirement there, it should be a one-on-one or one-to-one. So that's one-to-one function. So I will actually have a horizontal line test. So as you can see here, you have only one intersection. So it means that the function, the red line here, which is y is equal to 2x plus 4, is a one-to-one function. Therefore, there is an inverse. If the function is not one-to-one, there's no inverse of that function. And that's what we said in the previous presentation. So mostly in graphing, you can analyze and you can actually solve the problem. But by showing also the solution, by interchanging the x and y, you can see how are you going to find the inverse of the function. Okay. By showing also the graph, you can test if the two equations are inverses or not. So for example, let's say I have to change my second function as plus 2 here. Purple line here, as you can see, there's no common intersection now between the y is equal to x and the two functions. So it means that these two functions, y is equal to 2x plus 4 and y is equal to x over 2 plus 2, are not inverses to each other. So when you say inverses again, if you take the inverse of this function, it should be the first function here. If you take the inverse of this function, it will give you this. But in this case, they are not inverses now. They will be inverses if I'm going to change that back to a minus 2. As you can see, there is a common point here, and that's how you know that they are inverses.